Hi, hello dear students. Welcome to our channel Maths with Panindra. In this video, I am going to discuss about what is the definition of sample space and examples for different experiments and having the sample space. See here, first the definition here. What is the definition of sample space? The set of all possible outcomes of an experiment is called sample space. The set of all possible outcomes of an experiment is called a sample space. For example, here 5 examples I am giving and I will give the sample space according to the experiment. When we toss a coin, the total outcomes are head and tail. Either head will come or tail will come. So, the sample space is denoted by S. In that sample space, what are the outcomes we are getting? What are the results we are getting? Head and tail. So, H comma T. This is the sample space of the experiment. The tossing of a coin, one coin. If you toss a coin twice, 2 times, that means here one coin, here one coin. If you toss the coin simultaneously, tossing of a coin. See here, what are the possibilities? Directly I am writing here. S is equal to. So, 2 coins are there with me. I am tossing the coins. So, we may get 2 heads. Again I am tossing. I may get 1 head, 1 tail. Again I am going to toss. These are the possibilities. Two coins only. It may be 2 coins. If you toss like this, 2 heads will come. Or if you toss 2 coins at a time, it may be one is head, another one is tail. And TH, one will be tail, another one will be head, and both will be tails. If you toss of one coin, one time if you toss the coin, we are getting how many possibilities? 2 possibilities in the sample space. So, in this case, n of s is equal to, how many are there? 2. When the tossing of a coin twice or 2 coins are tossed, what are the possibilities here? N of s is equal to, in this case, 1, 2, 3, 4. 4 we are getting. That means 2 square. If we toss a coin 3 times, like this, 3 coins, one other hand take, other help, and tossing a coin, these are the possibilities we are getting. S is equal to, first one, all the heads, H, H, H. Second one, H, T, T. Next, this H will come in the second place, like this you can do that. T, H, T. Next, this H will become last. T, T, H. After that, all T's will come. T, T, T. Next, T, H, H. Next, this T will become in the second place. That means T, H, T, H. Next, this T will become last. H, H, T. Once you check that 1, 2, 3, 4, 5, 6, 7, 8. 8 possibilities are there. Can we write like 2 power 3? 8. Similarly, generally what we can conclude here, note. When n coins are tossed, when n coins are tossed, the total outcomes, the total outcomes is equal to 2 power n. You make a note. Suppose if it is 1 coin, 2 power 1. If it is 2 coins, 2 power 2. If it is 3 coins, 2 power 3. These are the ways. I hope you people understand, dear students. We will move on to the dice. So dice, you know that it is like a cube. If you throw a die, either the upper face will come from 1 or 2 or 3 or 4 or 5 or 6. These are the possibilities. So when one die is rolled, the total outcomes are S is equal to, in this sample space, in this case, 1, 2, 3, 4, 5 and 6. How many possibilities are there? 6 possibilities are there. Therefore, in this case, n of S is equal to 6. So, the number of things in the sample space, n of S means cardinality of the set. So, n of S is equal to 6. When 2 dice are rolled, then the total outcomes are. So 2 dice means here 1 die, here 1 die. Throwing a die, throwing a die. 1, 1, it may get. It may get 1, 2. It may get 1, 3. It may get 1, 4. 1, 5, 1, 6. Like this. 2, 1, 2, 2, 2, 3. Like this. So the sample space, observe carefully, I am writing here. So S is equal to 1, 1, 1, 2. 1, 3, 1, 4, 1, 5, 1, 6. So next it may get 2, 1, 2, 2, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. Like this. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. This is the way we may get 4, 1, 4, 2, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. Similarly, we may get 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. It may get 6, 1. Total 6 numbers are there, no? So 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. These are the total possible outcomes when 2 dice are rolled. So total 36 are there here. So 36 can be written as 6 square. That implies that n of S is equal to 6 square, which is equal to 36. So when 3 dice are rolled or 3 dice are thrown, you will get 6 power 3. That means 216 possibilities. Like 1, 1, 1, 1, 1, 2, 1, 1, 3. Like this it will be. Like 216 we have to write it. So generally, make a note another one. When n dice are rolled, when n dice are rolled, the total outcomes, the total number of outcomes, the total outcomes 6 power n. If it is 1 dice, 6 power 1. If it is 2, 6 power 2. If it is 3, 6 power 3. Like this it will be. I hope you people understand that about sample space and examples and different concepts and the definition of probability, mathematical definition of probability I am going to discuss in this. The next concept, dear students, classical definition of probability. This is the definition of probability we are discussing. So what is made by probability of the event? If there are n mutually exclusive equally likely and exhaustive events of a random experiment. In the first video of probability, I already discussed about exclusive, exhaustive and equally likely events. What is meant by equally likely events? Happening of equal chances. Happening of equal chances. The type of events are called equally likely events. Mutually exclusive events. The events are said to be mutually exclusive if the intersection of the two events is disjoint. A and B, A intersection B equal to 5. 5 means null set. And what is the meaning of exhaustive events? The union of events is equal to sample space. Suppose in the sample space two events are there, E1 and E2. The union of E1 and E2 is equal to sample space. Yes, then that events are called exhaustive events. So these events are there. In that experiment, total n events are there. Out of n events, m events are favorable to that. Out of n, m are favorable. So I have 6 marbles. In that 6 marbles, the other person want 3 marbles. So requirement is how much? 3. Total is how much? 5. I have 5 marbles. Other person wants 3 marbles or 2 marbles suppose. So requirement is 2, total is 5. So 2 by 5. Like this way. If there are n mutually exclusive, equally likely and exhaustive events of a random experiments and m of them are favorable to the event E, then the probability of occurring or happening an event E is denoted by P of E and defined as the number of favorable outcomes by total number of outcomes. Total I have 5 marbles. They are asking 3 marbles. So favorable is 3, total is 5. So 3 by 5. This is the way we can give that answer. So probability of the event E is defined as number of favorable outcomes divided by total number of outcomes of the sample space or random experiment. So simply we can write it as P of E equal to M by N. M are favorable cases, N is total number of cases. For example, when a coin is tossed, the probability of getting a head is. So when one coin tossed, what is the sample space? S is equal to, we have only H comma T. So total how many are there? N of S. N of S is total number. Total number is 2. 2 possibilities are there. But the requirement is what? Toss is the probability of getting a head. Requirement A is equal to, you take that A is the event. A is equal to requirement only H. How many are there? N of A is equal to only 1. So therefore the probability of the event A is P of A is equal to N of A by N of S. So N of A is 1, N of S is 2. So 1 by 2 is the answer. This is the way you can give the answer, dear students. I hope you understand that. So once again I repeat, when a coin is tossed, the probability of getting a head. So when the tossing of the coin, the possibilities are H comma T. So total N of S is equal to 2. The probability of getting a head, only one head, when we are getting only one possibility. Among the two, only head is one possibility. So H, A is equal to H. Favorable cases are what? Only one. So number of favorable cases 1 divided by total number of cases is 2. So this is the way. P of A is equal to N of A by N of S. N of A is favorable outcomes. N of S is total outcomes. Come to the second example. From the set of S is equal to here 1, 2, 3, 4, 5, 6. The probability of getting a prime number. So among these, what are the prime numbers? So let A be the event of getting a prime number. 2, 5. Even 3 also. 2, 3, 5. So these are the prime numbers. N of S is equal to total possibility 6. N of A is equal to favorable outcomes 3. So N of A is equal to 3. N of S is equal to 6. So therefore probability of A, P of A is equal to N of A by N of S. So N of A means 3 by N of S is 6, 1 by 2. Think you understand, dear students? We'll move on to the next question. If the question is like this, from a bag containing 4 white, 5 red balls, 4 white, 5 red balls, the probability of getting red ball is, the probability of getting red ball is. So total how many balls are there in this? So total balls, total 4 plus 5. 4 white balls, 5 red balls, that is equal to 9 balls are there. But the requirement, this is total. Therefore, N of S is equal to, out of 9 balls, we can select 1 ball. It is in NC, 9C1 ways, 9 balls. The probability of getting red ball, how many red balls are there? 5 red balls are there. So, A be the event of selecting the red ball. So, N of A is equal to, directly write it. Among that 5, we can select 1. 5C1, which is equal to 5. Therefore, the required probability, P of A is equal to N of A by N of S. So N of A is equal to 5. N of S is equal to 9. Therefore 5 by 9. This is the probability of getting a red ball. So total number of balls. And how many are favor here? Probability of getting red ball. How many red balls are there? 5 red balls are there. Out of 5 red balls, 1 red ball we can select. So 5C1, out of total 9 balls are there, from that also we can select 1, 9C1. So 5C1 by 9C1, which is equal to 5 by 9. Like this way we can apply the definition of probability, we can define. Now we will discuss the important points. What is the important points here? In these important points, the first one is P of E is equal to, P of E is equal to the probability of the event. The probability of an event. So E be the event. In an experiment, these are the, in this experiment, total n things are there, n things are there, total n things are there. Out of n things are favorable. So the probability of the event is, total n favorable is m. Next, this is m by n. P of E is equal to P of E bar or E complement or P of E bar. The probability of, the probability of, the probability of not getting an event, not favorable, not favorable, equal to, observe carefully dear students, here only, total events are n. Out of n, m things are favorable means the rest of the things, n minus n thing is not favorable only, no? Out of n things, m things are favorable. So n minus n things are not favorable. So not favorable is n minus m. So from here only we will define, observe carefully. So P of E bar or E complement. P of E complement is equal to n minus m divided by n. So we can write it as n by n minus m by n. That is equal to n by n means 1 only, no? Minus m by n. M by n means what? P of E. So P of E complement is equal to 1 minus P of E. This is the very important result, dear students. Probability of not happening or not favorable. P of E complement equal to 1 minus P of E. From that we can write another result. P of E complement, P of E minus P of E we can take this side. P of E plus P of E complement is equal to 1. That means the probability of favorable events plus the probability of not favorable events is always equal to 1. Keep in mind, dear students, this is very important property. Some cases P of E is equal to, they are considering as P as a success, and P of E complement or P of E bar they will consider as Q, that is failure. So according to this, probability success and failure is equal to 1. You remember, this result may help you. Number of problems we are going to apply this property. P of E plus P of E complement equal to 1. For example, S is a sample space. S is a sample space of the random experiment of rolling a die. So rolling a die means S is equal to 1, 2, 3, 4, 5, 6 will come. What is the probability of getting the number 1? What is the probability of getting the number 1? So S is equal to sample space. For example, I am saying the probability of getting a number 1, the probability of getting a number 1 when tossing a, when throwing a die or rolling a die. Rolling a die. So in the sample space, S is equal to, when rolling a die, what are the possibilities? 1, 2, 3, 4, 5, 6. So n of S is equal to 6 possibilities are there total. Here the case is getting the number 1, only 1. E is equal to, what are the favorable cases? Only 1. So probability of E, P of E is equal to, from this n of E is equal to how many numbers are there favorable? 1. P of E is equal to n of E by n of S is equal to 1 by 6. Suppose in this question, the probability of getting a number other than 1 if they will ask. Other than 1 if they will ask in this question. How we are going to use this concept that I am explaining, dear students. Find the same question if they will ask. The probability of getting a number other than a number 1. Other than a number 1. That means either 2 or 3 or 4 or 5 or 6. So other than the number 1 means what? The rest of the numbers only, no. So that time, after getting of this result, E bar is the event, E complement is the event of getting other than 1. Other than 1. So other than 1 means the rest of the only, no. So P of E complement is equal to, by using this formula, P of E complement equal to 1 minus P of E. P of E is what? Getting a number 1. 1 minus, get P of E value is 1 by 6. So 1 minus 1 by 6 is 5 by 6. So the probability of getting other than number 1 is 5 by 6. Getting the number 1 is 1 by 6. So that is the use of this property. P of E complement equal to 1 minus P of E. And in some of the cases, we'll take the favorable cases. That means P of E we can take as a means occurring, non-occurring, happening, not happening. P of E is happening, P of E complement is not happening. P of E is success also we can take P. P of E complement Q, failure we are taking. Sum of the failure and success of the probability is always equal to 1. And this probability, any probability is always lies between 0 and 1. So the probability of an event, 0 is less than probability of E is less than or equal to 1. This is very important result, dear students. And every probability, any probability event is always lies between 0 is less than, P of E is less than or equal to 1. So that means maximum of the probability is 1. So always lies between 0 and 1. It should be less than or equal to 1. Yeah, keep in mind, dear students. We'll move on to the different concepts, including some definitions, some different concepts also I will give it. Yeah, here one more result. And probability of the sample space is always equal to 1. Sir, how it will be the probability of the sample space is 1? So for example, sample space means all the outcomes of the experiment. Suppose if you conduct an experiment of a tossing of a coin twice, so HH, HT, TH, TT, like this 4 will come now. P of S is equal to favorable outcomes 4, total outcomes also 4, 4 by 4, it will become as 1. For example, take this set. From the set, S is equal to 1, 2, 3, 4, 5, 6. Find the probability getting the numbers 1, 2, 3, 4, 5, 6. Getting all the numbers they are asking. So that time, favorable events also 6, total numbers also 6. So P of S is equal to 6 by 6. So that is the reason the probability of the sample space P of S is always equal to 1. Suppose in the sample space 2 to 3 sets are there. A union B union. Suppose A set, B set, C set. A union B union C is equal to S. Why? Because mutually exhaustive events. A intersection B, B intersection C, C intersection A, which are disjoint, exclusive events. And whenever like this, it will be there, equally likely, also possible for that. So, that time, A union B union C is equal to S. So, taking probability on both sides, P of S is equal to P of A union B union C. P of S is equal to P of A union B union C. So P of S is equal to 1. So probability of A union B union C is also equal to 1. Sometimes only 2 events are there in this S. P of S is equal to P of A union B. Like this we can take. This value is always 1. And some important results, set theory as well as probability, that we will discuss now. Yeah, next concept, dear students. Axiomatic approach and probability function. Generally, just probability definition, classical definition, and then directly we'll enter into the problems. But a little concept about axiom approach. What is the meaning of axiom? In mathematics way, a statement without proof is called an axiom. So unprovable. So we can assume that. So probability function in that very important. Everything we are writing P of A, P of B, like P of E, we are saying no, that is probability function. That P represents probability function. What is probability function? Let S be the sample space of a random experiment. Then a function P here, probability function. Defining from sample space to R. P of S is the sample space to R, satisfying the following axioms is called probability function. So whenever the P of S is satisfying these, then it is called probability function. In that first one, axiom of non-negativity. Axiom of non-negativity. Suppose E be the any event in the sample space S. So this probability, the probability of the event E is denoted by P of E, which is always greater than or equal to 0. Whenever it is greater than or equal to 0, then only it is non-negative. For all events belongs to sample space or probability function. So event. So greater than 0 means okay, positivity will come. But what about equal to 0? Whenever the probability of the event is equal to 0, then it is called impossible event. P of E is equal to 0 is called impossible event. Impossible event. The probability of getting the probability of getting here, suppose for example, how it will be P of E is equal to 0. E is equal, S is equal to sample space I am taking, S is equal to 1, 2, 3, 4, 5, 6. It shows that sample space containing 6 numbers means a dice. Throwing a die once. S is equal to 1, 2, 3, 4, 5, 6. The probability of getting the number 7 if we throw a die. So if you throw a die, what are the possibilities? 6 numbers only. But they are saying that the probability of getting the probability of getting the number 7. Is it possible? Out of 6, only 6 numbers only possible. How you are getting the number 7? It is not possible. That is the reason that event is called, that event possibility, probability is 0. There is no case will arise to get the number 7. That type of event is called impossible event. The probability of getting the number 7 other than these 6, whatever the number they are asking, that is called impossible event. So this you leave it. I want to explain for the concept of P of E is equal to 0 what happens. Anywhere it is non-negativity, negative is not there, greater than 0. Any probability is always greater than or equal to 0. E should be belongs to probability function and it should be belongs to sample space, the event. Now come to axiom of certainty. Just now I discussed in the previous concepts. Axiom of certainty means the probability of the sample space is always equal to 1. The probability of sample space is always equal to 1. So here S is containing 6 numbers. The probability of getting the all 6 numbers. So 6 numbers, 6 by 6. Favorable cases by total number of cases. 6 by 6 is 1. This is called axiom of certainty. Suppose in the sample space S, E1, E2 are the two events. E1, E2 is equal to S. So taking probability on both is P of E1 union E2 is equal to P of S. That value is equal to 1. This is called mutually exhaustive events in that case. Now come to axiom of union. E1 if E1 comma E2 or any two events of a sample space, two events of a random experiment of a sample space, events of a sample space of the random experiment, events of a sample space of an experiment and E1 comma E2 are mutually exclusive. That means exclusive means what? E1 intersection E2 is equal to 5. So that time axiom of union means probability of E1 union E2 is equal to, we can write it as P of E1 plus P of E2. Whenever E1 E2 are mutually exhaustive, the probability of union of these two events, we can write it as probability of E1 plus probability of E2. Whenever E1 E2 are mutually exclusive, even exhaustive also it will be applicable. So that time we can write as P of E1 union E2 is equal to P of E1 plus P of E2. I hope you understand that, dear students. After that, I will explain the addition theorem on probability and some examples based on that. Addition theorem on probability for the two events, addition theorem on probability for the three events. The total concept I am going to explain here. Yeah. The next very important theorem, dear students, in the view of public examination or competitive exams based, this theorem statement is very important. Sometimes in the boards, in the public examinations, they will ask like this: state and prove addition theorem on probability. They won't give the statement sometimes, or this is the way they will ask it sometimes. If E1, E2 are two events of a random experiment and P is a probability function, then prove that P of E1 union E2 is equal to P of E1 plus P of E2 minus P of E1 intersection E2. In this proof of addition theorem on probability, we have two important cases. Two cases are there. One case is the events mutually exclusive. See here, E1, E2 or any two events. Let E1, E2 or any two events of a random experiment and capital P is a probability function. Is a probability function. In the case 1, if E1 intersection E2 is equal to 5, in this case E1 intersection E2 equal to 5 means these are disjoint sets. So case 1, observe carefully, dear students. This is the sample space of random experiment. Yes, E1, E2. So E1 and E2. There is no common place. That is the reason E1 intersection E2, we are saying that. That means these two events are disjoint. They are asking probability of P of E1 union E2. They are asking to prove this result. P of E1 plus P of E2 minus P of E1 intersection E2. See here, probability of E1 union E2 is equal to P of E1 plus P of E2. Sir, how you are writing, sir, directly? P of E1 union E2 equal to P of E1 plus P of E2. Just now, before the discussion of addition theorem, axioms we discussed. What axiom? Union axiom. The property. Axiom of union. In the axiom of union, the probability of E1 intersection E2 is equal to, E1 intersection E2 is equal to 5. Probability of 5, probability of null set is equal to 0. So P of E1 intersection E2 equal to 0. P of E1 union E2 equal to P of E1 plus P of E2. That is called axiom of union. So can I write like this? P of E1 plus P of E2 minus 0. Can I write like this? To prove this result, in place of 0, P of E1 intersection E2. Why? Because these are disjoint, mutually exclusive events. Since E1, E2 are mutually exclusive. Exclusive events, that is the reason intersection is pi. So in place of 0, we can replace with this. So P of E1 plus P of E2 minus P of E1 intersection E2. In first case 1, the result was proved. In the case 1, when E1 intersection E2 equal to pi, the statement was proved. We'll take that second case as E1 intersection E2 is not equal to pi. I will rub this and I will discuss the second case. This case 1, this is the case 1, dear students. I hope you people understand. This case 1 is also important. Case 1 as well as case 2. Both are important. Yeah, in the second case, case 2, in this case, E1 is intersection, E1 intersection E2 not equal to pi. So, the figure will come like this. This is the sample space. E1, E2. E1 intersection E2 is not equal to pi. Why? Because this is a common part. This is called E1 intersection E2. So here E1 union E2. E1 union E2 can be written as E1 union E2. Observe carefully, dear students. This part, in this E1 event, E2 is not including, no? So till here means it is only E1, E2 not included. E2 not included means E1 minus E2. This part is E1 minus E2. So E1 union E2 can be written as this part, E1 minus E2, and this is E2 now. This is completely E2. So E1 union E2 can be written as E1 minus E2 union E2. E1 union E2 can be written as E1 minus E2 union E2. That means the combination here, the sum of two events we are writing, the union of axiom. Taking probability on both sides, P of E1 union E2 is equal to, taking probability on both sides, P of E1 minus E2 union E2. These two events, why we are writing like this? Even these two also mutually exclusive events, and these also disjoint events. There is no common part. From here to here, E1 minus E2. From here to here, it is E2. There is no common part in this. Observe carefully. From here to here, absolutely, and from here to here, there is no common. These, since E1 minus E2 and E2 are mutually exclusive. Mutually exclusive. That is the reason we are writing like this. Again, by using axiom of union. Axiom of union. This can be done as P of E1 union E2, E1 minus E2, P of E1 minus E2 plus P of E2. So P of E1 union E2 is equal to P of E1 minus E2 plus P of E2. By using this axiom of union, put that as equation number 1. But how it will come E1 minus E2? How we will get E1 minus E2? The first case is very easy, considering E1 intersection E2 equal to pi, and we got within 2 steps we got it. But in the second case, E1 minus E1 union E2 can be written as the union of these two events or sets. After that, applying probability on both sides. By using axiom of union, this can be expressed as P of E1 minus E2 plus P of E2. Keep it as equation number 1. Now, to get P of E1 minus E2, E1 can be written as, this part is E1 intersection E2 only, no? This is E1 intersection E2. So E1 only can be expressed as even the union of these two, and these are disjoint events. Again, they are mutually exclusive. So again, consider E1 can be written as E1 is equal to only E1, the union of these two, E1 minus E2 union E1 intersection E2. I hope you people understand from the figure. E1 can be expressed as E1 minus E2 union E1 intersection E2. Since both E1 minus E2 and E1 intersection E2 are mutually exclusive. So whenever mutually exclusive, this intersection is equal to pi, obviously. So whenever this intersection is pi, by using axiom probability, by using axiom of union, taking probability on both sides, P of E1 is equal to probability of this E1 minus E2 union E1 intersection E2. So by using this probability, by using axiom of union, this can be expressed as P of E1 is equal to P of E1 minus E2 plus P of E1 intersection E2. P of E1 equal to P of E1 minus E2 union P of E1 intersection E2. That can be written as, by using this axiom of union, P of E1 minus E2 plus P of E1 intersection E2. From this I want P of E1 minus E2. Make as a subject. P of E1, this P of E1 intersection E2 we can take this as minus P of E1 intersection E2 is equal to P of E1 minus E2. Put as equation number 2. Equation 2 substitute in equation 1. Here I will give that equation 2 substitute in equation 1. Equation 2 substitute in equation 1. We get P of E1 union E2 is equal to, in place of P of E1 minus E2, you have to replace with this P of E1 minus P of E1 intersection E2 plus P of E2. Write in the order. P of E1 union E2 is equal to P of E1 plus P of E2 minus P of E1 intersection E2. So hence the result in the second case. Even in the second case also, we proved when E1 intersection E2 is not equal to pi. These are the two important cases, dear students, in the addition theorem on probability. I hope you people understand that. In any other video or in any exercise, I will cover the addition theorem on probability for the three events A, B, C. That means P of E1 union E2 union E3, like P of A union B union C. That also I will cover in the coming videos. Thank you for watching. Still, if you have any doubt regarding this, you can write to my comment box. In my free time, I will respond. Thank you. Signing off, Maths with Panindra. Jai Hind.